University of Sydney, who will tell us about universal generalized lattice surgery. Please take it away.
Okay, thanks, Nico. Yeah, I guess it's going to be pretty casual, so please feel free to ask questions as I'm going. I'm going to talk about this work, and I'm happy to talk about it here because I did this work here. So my thanks to my collaborators and also to the organizers of the program last year. And I think there's a high chance I wouldn't have thought about these things if I wasn't spending a few months here with some of these people. So there's a couple of works I'm going to talk about, mainly the first one with Ted Yoder. I'll touch on this other work that has Ted and these two students. Sonny's here, so you can ask him, and he's going to give the next talk, which will cover this work in more depth. And then I'm going to touch on this work with a bunch of authors that we also did part of here. Okay, great. What's the motivation, right, for what I'm going to talk about? I'm going to talk about this sort of generalization of logical gates from surface code to more general LDPC codes. And the idea is there's been a bunch of work on trying to find better alternatives to the surface code. I think it's still really an ongoing area of research to make these things practical, but there's been a bunch of really promising theoretical results. But we still have this challenge of just finding memories that are really going to outperform surface code in practice, but we don't want to just store quantum information, we want to do logic on it. And there's been a lot of work on optimizing logical operations on the surface code. One of these popular methods is known as lattice surgery. I'll explain what that is, and I assume everyone is totally familiar with that. And this talk will be about basically taking that method and generalizing it to apply to really a broad class of QLDPC codes, so that whatever code we kind of land on using in the end, we can apply these methods. So we're not going to be like focusing on a particular code, unlike this case where surface code was the focus. Great. Yeah, I was giving this talk a bit last year, and people kept asking, like, there's so much going on in lattice surgery. I don't know if people are following. Maybe you've seen a bunch of papers come out, and they're like, what is going on? So I made a bit of a timeline. But before I do the timeline, I think I just want to say, what is lattice surgery, just to set some background. So I was a bit too lazy to fill in these surface code patches, but the basic idea is you have two surface code patches. You actually don't need to know all that much about what the surface code is, except it's an LDPC code, so it has low density parity checks, and it has some logicals, and we're going to look at addressing two of these logicals. So it has this sort of planar layout. It fits in a nice 2D grid with local checks, and you have these logicals supported on the edges. And often in surface code, you want to do everything in a 2D planar layout because that's what you imagine your hardware constraints are, or people were imagining that for a long time. And this is a nice method to basically take. You can see that you can put two of these logicals kind of right next to each other if you put the surface codes next to each other. So you think I should be able to measure those two logicals or act on those two logicals together somehow. And that's what lattice surgery lets you do while maintaining the QLDPC property. You basically just make one bigger surface code. You fill in this region in between the two logicals with more of your lattice, and you just measure into the surface code checks there. And what this does is makes one big patch of surface code. So you drop from one logical per patch, which would be two, to a single logical in this bigger patch. You get a measurement outcome, which is that from all these local measurements you do, you can infer this big logical x1 times x2 on the two patches. And then you can, so yeah, at this point, you're not really in the original code space. You're in like this joined surface code. To return to the original code space, you just measure out these qubits along the edge in the right basis. And that restores your original surface codes, except now you have this measured x1 times x2 logical. So you can kind of boost this up into being a scheme to do essentially all of your Clifford computation on surface codes while remaining planar. And you can do fancy things like routing these patches in between around to join things that are far away. I'm not really going to go into this, but there's a whole literature on tricks with lattice surgery for surface code. So it's kind of a really, really useful thing to do planar computation. Great. Okay, back to my timeline. So hopefully we're happy with what lattice surgery is. Feel free to ask questions if that is not clear already. And yeah, so what happened between then and now? Well, I wanted to have a bit of prehistory too, since we're in the Bay Area. Before lattice surgery, we had the Summer of Love, and then there was lattice surgery. And then last year, there was the Summer of Lattice Surgery. So it's pretty similar. I don't know if you can see the parallels. All these happy people, I don't know. Here we were high in the mountains. There, I don't know. We were in Dolores Park or whatever. And a bunch of people somehow all managed to, or so it was something in the air, we're all working on lattice surgery last year, and that's why all these results have come out, and we weren't necessarily talking to each other. That's why it's all a bit confusing, because it was just sort of the right time to do these things, and not all the authors talked to each other, and now we're kind of comparing notes, I guess. So let me do that for you. A more serious history. Yeah, we have this surface code version of lattice surgery more than 10 years ago. And then there's a whole bunch of stuff in these dots. So even beyond this period, people were still improving and finding new things to do in surface code lattice surgery. There were some more general works looking at other topological codes, such as this one. And then we kind of move into the more general QLDPC era, where people are thinking about techniques to do on codes beyond the surface code. And a first relevant work was by Hastings. He has these weight reduction works where he's thinking about taking checks that might be very big and enforcing them by a product of local checks, basically. So you can imagine, what if my big check is the logical I want to measure, and I enforce it by a bunch of local checks? It's very similar to lattice surgery. And this nice scheme that people call the Cohen scheme, or the Larry gate, or the CKBB scheme, I see Isaac sitting right there, so I don't want to say anything bad about it. It's a very, very good scheme, and it was like a kind of breakthrough work to really make this idea serious of taking the weight reduction idea and using it to do lattice surgery on a general QLDPC code. So why do we keep working on this since we have this nice scheme? Because it turns out the overhead in this scheme is kind of good for hypergraph product codes, and we'll see this later in more detail. But almost the same month, or the same maybe a month later, this good QLDPC work came out, and we now had codes that had better distances than hypergraph product codes. And it turns out the overhead here is kind of prohibitive for measuring the logicals in these codes. So we needed some new techniques, and that led to a whole bunch of people thinking about this over the next 2 years, basically. So there's been a bunch of works kind of improving the scheme, finding different schemes, and I'm going to talk about this one, where we used an idea from physics called gauging, where you use sort of gauge symmetries and lattice gauge theory. So we took these ideas and applied them to this lattice surgery procedure to find a more flexible way of doing it. So this, in the end, let us sort of reduce the overhead in the worst case. And there's a sort of simultaneous work by a group at Xanadu. So at the time I did this, I should say, I was at IBM working with Ted, who's also at IBM. And there was this work from Xanadu we found out about like the week we posted, which is like a different way of formulating something quite similar. But I'm not going to talk about their way of formulating it because it's my talk, so I'll do what I want. But yeah, essentially it's equivalent up to some asterisks. And following this, there's been, so this wasn't the end of the story. This was kind of like a primitive, these two works. How do you like measure one logical in a very efficient way? That's not really getting you to computation. There's a whole bunch of questions that come out of that, which is how do you do things in parallel? How do you measure logicals that are not Pauli's to do universal computation? How do you build an actual architecture about this, which Sunny's going to talk about a lot more? Yes, okay. And in this talk, I'm going to focus on this first work and this fourth, most recent work. So the first work is like this primitive operation that I'm going to talk about for most of the time, which is how do you just measure a logical in a QLDPC code in this way by thinking about it as a symmetry and turning it into a gauge symmetry. And then I'm going to talk a bit about a part of this work. So this more recent work is like sort of super expansive and has a bunch of cool physics and stuff in there. I thought it maybe wouldn't fit the audience as well to go into that in great detail. So I'm going to try and sort of pull out the part of that that's most related to lattice surgery, which is not the whole paper. So in case my co-authors watch this, I don't want to get angry and say, you didn't talk about all that other cool stuff. Yeah, sorry, maybe one of you can come and give a talk here soon. I'll just talk about part of this paper that's very related to lattice surgery. Great. And then, yeah, if you want to know about parallelism, in this whole talk, I'm just going to be talking about measuring one logical. Parallelism, we have thought about that, ask me later. And if you want to think about, well, sure, you said measure one logical, but I want to do computation, measure different logicals. How do you like build a system that can do that? I might talk about that for like one slide at the end, but Sunny's going to give a full talk on that next, so stick around in case you're planning to go anywhere. Good. All right, so a bit of context for why are we talking about measuring logicals in QLDPC code so much, and why is this like an important problem? Usually we have this sort of standard gate model for thinking about quantum computation, where we compile everything into Clifford gates plus T, probably have some standard single and 2-qubit gate set for the Clifford gates even. So I'm using this nice notation from this paper by Latinsky. And yeah, you can see you can compile everything into these basically pi/4 rotations and pi/8 rotations. The pi/4 are your Cliffords, pi/8s are your T's, and then you have these Pauli measurements, or these blue boxes at the end of the computation. And the idea is that in like a good code, there's no real meaning to, well, there's not really a clear meaning to this division into qubits, these logical qubits, right? You want to do this whole computation fault tolerantly. These qubits are living in a code block. Maybe they all live in the same code block. Unlike with surface code, there isn't this nice basis where there's like one logical qubit per code block. And this division into these qubits is like pretty arbitrary. So there's no real advantage to compiling into these low weight gates on the qubits. You might as well just compile out all the Cliffords and just have these Pauli rotations around arbitrary Pauli strings, because they may just have the same physical weight. Even though this looks big on the logical qubits, if you have a good code where all the logical scale with the same distance, this logical may be the same weight as like a single qubit logical in your basis you've chosen. So this is kind of being quite agnostic to the code. If you know a lot more about the code, probably you can pick a good basis, but we're not assuming any knowledge of the code. Great, so you compile out all the Cliffords and you're just left with a bunch of pi/8 rotations and then Pauli measurements. And then you do this trick to basically do gate injection. So instead of doing the pi/8 rotation around a Pauli directly, you turn it into 2 Pauli measurements. There's like this frame update, which you can kind of keep track of classically, and there's a magic state preparation. And in this talk, I'm actually going to talk about both bits, but for the first part, I'm going to focus on this Pauli measurement. And what we really want to do, if we turn all of our computation, all of our fault-tolerant computation into these Pauli measurements, is really minimize the overhead on these Pauli measurements. And we're going to focus, I'm going to start by focusing on the qubit overhead, because that's sort of generally, at least nearer term, like the thing that probably is going to cost the most. And I won't dwell on that too much. Improving the time overhead is also an important problem, but not something I'm going to talk about much in this talk. Okay, great. And then in the second part of the talk, I'll talk about these magic states a little bit, comparing those. Good, so let's start with this. I'm going to tell you about this paper, how we took this idea of turning a logical operator into a sort of gauge symmetry and use that to do lattice surgery, to give us this sort of primitive operation to do lattice surgery on any Pauli logical in a code block. Good, so the main result, the headline is, we have this general fault-tolerant scheme that applies to QLDPC codes, so codes that have a sparse tanagraph, and it gives you a logical measurement of any Pauli, but okay, here I've phrased it for a Pauli with the minimal distance, but say it's a good code, this would be any Pauli, with this overhead. So you really want to get down to the overhead of just the distance. That's like you've kind of just put qubits along, you've put ancilla qubits along the place where the logical is, which is pretty reasonable. But we have this log cubed factor, which I'll tell you about in the worst case at least later. But this is a big improvement over previous work where you had this sort of d squared factor, which is kind of like you're attaching a planar thing to the logical rather than something more linear or sparse. Good. And yeah, something else that's an important point, I guess I'm kind of going to focus on the theoretical aspects, the worst case behavior, but this has actually ended up being kind of useful, surprisingly to me, that you can go and take this procedure we've defined, which has, you'll see in a minute, like quite a general graph input, and instead of like picking some construction that works in the worst case with a guarantee, you can kind of have a heuristic to try and pick a good graph, and it works, there's different heuristics, and they end up working quite well if you just do something quite dumb and random, and then just check if you kind of got a good result, and then just repeat if you didn't. And so it ends up being quite useful in practice, at least on small instances, to find good surgery ancillas. So that's an important point I won't talk about too much more in this talk. I'll focus on the theory, but yeah, maybe this is actually more important than the worst case guarantee. Oh, good. I added this comment because people seem to miss this point. Sorry if it's a bit low, people can't see it, but basically, I've phrased the result here for measuring a logical with a distance, but maybe you have a code where not all logicals scale with the same distance, and there's some logical weight that's called W. Maybe even you have multiple code blocks and you have a logical across the code blocks with some distance that I'm going to call W. And then you can still apply this scheme to such things. Then in that case, the scaling you get is W log cubed W. So, and this is comparing to the old scheme is still an improvement. There you would get W times D. Okay, so that's like the headline result. Any questions about the statement of the result? Or I'll move on to how it works. Good. Okay, so I'm going to take my notation and simplify it a bit. Instead of having this picture of this bicycle code from IBM, it's going to draw a gray block. It's very imaginative. And that's because I'm going to put some extra stuff on top of it. So yeah, keep in your imagination some arbitrary QLDPC code here. And what I want to know is, okay, I have some logical operator that I want to measure. I should have said in the result statement, this applies to non-CSS codes as well. So up to a basis change, I can assume my arbitrary Pauli logical is just an X logical operator. And it's supported on some set of qubits. I'm going to draw its support in blue here. And the qubits are these little dots. Great. And the motivation, so I'm going to try not to use too much physicsy language and explain things in terms of a graph in a second, but the motivation was really from physics. So some things going on in physics were people were looking at basically making exotic states by gauging symmetries. And the idea of that is you have some big operator that commutes with the Hamiltonian. Here, your Hamiltonian you could think of as the stabilizers defining the code space. You have this big operator that commutes with them, the logical operator. And you want to turn this big operator, distance d, maybe d is scaling like n, into essentially you want to make a new system where this is enforced, like you get an eigenvalue of this guy, via a product of local operators. And this happens in this setting of gauging a symmetry. You basically take a big operator that you want to commute with the Hamiltonian, and you enforce that via a bunch of small operators that commute in the Hamiltonian. So for us, we're going to, instead of having a Hamiltonian, we're going to do this in the stabilizer group. We're going to basically make a new code, add stuff to the stabilizer group to enforce this big operator, inspired by this kind of lattice gauge theory approach. And if you like, I'm going to try to stick to the quantum computing terminology, but in the sort of lattice gauge theory formulation, there's like a dictionary to all of the terms we're more familiar with. So like matter degrees of freedom in lattice gauge theory would be like the physical qubits for us. Gauge fields there are going to be like our ancilla qubits. The global symmetry that we're going to be gauging is a logical operator. And these local gauge symmetries will be new stabilizer checks we add. Cool. So if you don't like physics, you could ignore this motivation. But anyway, this is what the motivation was. And yeah, now let me explain it in terms of a graph. Cool. So we have our logical operator. And we're going to take like the vertices, or we're going to take the qubits in the logical operator support, make them the vertices of this graph. You can kind of, formally you can add extra vertices by just putting ancillas that are decoupled from the code, so you're not restricted to only have vertices inside the code. That's like a minor point that's kind of important later for the worst case result. So you take this graph, and here is where the choice is. Instead of fixing some graph depending on the code properties, you're allowed to pick whatever you want. It should be connected if you want to measure this logical, but you could even pick something disconnected and you measure something different. Okay, and so you take this graph you're allowed to pick, you slap it on top of the code, and it's going to tell you how to make the procedure, or how to go about the procedure. So this graph is your guide, and what you do in the first step is initialize new qubits. So you have these original qubits of your code in the logical support. You add a new qubit for every edge. This is kind of like Torah code. You have a bunch of edge qubits on this graph, and you initialize them in the 0 state. Then for the code deformation step, so now you're making a new code. I've like noted you have a deform code. To do the code deformation, you measure a bunch of these vertex checks. So these vertex checks are going to measure one of the x's from the logical support, together with all of the edges, x on all the edges, the edge qubits that touch that vertex. So you just go ahead and measure that on all of the vertices. And this does your code deformation. You now have a new code. And you can see that at this step, if you take the product of all of these vertices, every edge, the x on every edge will get canceled because you have no dangling edges, and you'll just be left with this big logical you wanted. So this is how these like local stabilizers enforce this large logical. So once you've measured these, you can infer the value of the logical operator you wanted, although you're in this different code. And let me just talk about what this different code is for a second. So I'm kind of being agnostic to what the original code was, except I want it to be LDPC. And what happens to the stabilizers in that code? So let me look at this like simple example. If I have X-type stabilizers, they just stay the same. If I have stabilizers with Z parts to them, so this could be a non-CSS code, so that could come in the form of Y operators or Z operators. But the overlap of these Y or Z operators always has to be even with this logical, because the logical commutes with the stabilizers of the code. And so you can kind of reduce this down to a base case of just a pair of z's overlapping with a logical. And if there's, say 4 z's in the stabilizer, you just pair them off into 2 pairs and apply this recipe. So for a pair of z's in one of the stabilizers of your original code, you have to, well, it gets addressed when you do the measurement. And what it gets addressed by is z's along some string connecting the 2 endpoints. Yeah, so what was before just a pair of z's now picks up this string of z's connecting them. This is like kind of dressing charges in lattice gauge theory, if you like that. And then you also pick up a bunch of cycle stabilizers. So these are just new stabilizers that are coming from the auxiliary graph qubits themselves, and they don't involve the qubits of the original code. And on some basis of cycles, you just have z checks around the cycles. Yeah, so this is basically everything in the new code. You have your original checks, you have these vertex stabilizers, the original checks with the z part get deformed, and you pick up these cycle stabilizers. Good, so people have questions about that, or is that clear? This is the deformed code you add in. So this is like the analog of in the normal lattice surgery, you merge 2 patches into one big patch. Here, it's not looking exactly like that. We kind of take a code and make a weird different code. All right, and then the final step is pretty similar to normal lattice surgery. You just measure out all the edges in the Z basis. And this restores you back to the original code. You can check that. But you keep this logical operator that you wanted to measure. So that's the only new stabilizer you pick up when you do this deformation back to the original code. You don't accidentally measure anything else, so long as the graph is connected. Oh yeah, so I have a slide for that. Cool, so the result of all this is that you can kind of check this carefully. What you get exactly from this sort of channel is that on your code, you get this projection onto plus or minus eigenvalue of this logical operator, which I'm writing as a product of x's. And the plus or minus is given by the product of the observed eigenvalues of all the vertex terms you measured. And then there's a Pauli byproduct operator I kind of skipped over, which you can keep track of classically. And let me not dwell on that. Good. All right, so I said there's an arbitrary graph. So if you had some numerical experiment, you could try and sort of look at the code properties of the deformed code, play around with the graphs to find a good one. But we want this worst case result. So what graph do I need to pick to guarantee a good worst case performance? As long as you have a graph with these properties I'm going to list, we can guarantee this worst case performance. And the properties are, okay, so you have to have this good edge expansion. I don't know why I wrote it this way. The Chiga constant has to be 1. So basically, when you take some set of vertices and then look at the weight of the adjacent edges, it has to not reduce the weight compared to the vertices. And this is to do this. The reason you want this is so that you preserve the distance of the code when you go to this deformed code. Because when you're changing a code, you could like sort of accidentally drop the distance, which would be bad. Okay, and I'll say a bit more about that in the fault tolerance slide next. Then the next 3 properties are all to do with keeping everything LDPC. So why am I focused on LDPC here and not talking about more general codes? If you don't have some restriction in your sort of physical model that you want to measure low weight things, you could just directly say, I just declare that I measure the logical operator. So to make this game sort of make sense, you want to focus on LDPC things. And to keep everything LDPC so as to not cheat and just trade off measuring one high weight operator for a different one, you need some properties of the graph to guarantee that. The first one is that it should be low degree. This is so this like vertex term you measured, the star term, is a constant weight. So you really want a constant degree graph, a sparse graph. You want this sort of short paths condition, I'm calling it, which means that when you have this 2 points getting dressed, so any 2 points from your stabilizers that land in this graph should be connected by a constant length path. Otherwise, you would pick up a big check in the deform code. And then you need short cycles, so you need a constant weight cycle basis. And that one is to guarantee that you have still an LDPC code when you add these cycle checks in. Okay, so if you can guarantee that with some graph, you'll end up getting this result. You'll end up getting a surgery measurement that preserves the distance and keeps the code LDPC. And what we can tell you is how to pick such a graph with this overhead. So if you want to measure a logical with weight d, you only need d log cube d extra qubits. So this is kind of a little bit worse than what we had hoped for. We hope to just kind of put down sort of a random expander on top of this set of qubits and hope that would work. That doesn't quite work because it fails short cycles essentially. And that's where this log cube D is coming from. You need to sort of fix this having short cycles or constant weight cycles property. Luckily, Friedman and Hastings solved this for us. So there's some procedure you can do to turn like a sparse graph into one with a low weight cycle basis. And we apply that, which is where this comes from. I'll show you that in the next slide. And again, this is an improvement of like a factor, or turning a factor of D into a log cube D. So it's pretty good, even in the worst case. And I'm not sure what the kind of lower bound would be for this surgery style thing. I think well, it's definitely D, but maybe you actually even will need one of these log factors in like for a general case. I'm not sure. So that's like an interesting question. If you have any thoughts on that, tell me later. Good. So I want to show you like a picture of how we come up with this graph that gives us this behavior in the worst case. So if we have some hypergraph that's like the support of our logical, how the checks overlap with that. First, what we do, so this might not be a graph, we need a graph. We break up the hyper edges into just some covering in terms of edges. Then this might fail the expansion test. So we go in and add some extra edges to increase the expansion. So there's some extra edges in this little picture. The problem with this graph we have now, we have some sparse graph, and it has good expansion, sort of by construction, but it may have like large weight cycles. So you could think this one in the middle, maybe it's too high weight for us. And to fix that, we use this decongestion lemma from Miss Friedman-Hastings paper, which is a nice idea. Basically, you can see if you have like some big cycle, if you just kind of triangulate that cycle, you can turn it into a bunch of low weight cycles. Sorry, you can enforce it via a product of low weight cycles if you just triangulate it into a bunch of triangles. The problem is that will blow up the degree. And Friedman and Hastings came up with this lemma that lets you kind of take copies of the graph, glue them together in a sort of obvious way, and then sparsify the cycles on different copies. So the key trick is how many copies do you need to sort these different cycles into the different copies, so that when you add these sparsifying edges to turn the cycles into low weight cycles, you don't blow up the degree. And it turns out the number of copies you need there is essentially log cubed of the size of the graph. So that's where that comes from. Yeah, so if our logical is weight W, the graph has W vertices, you need log cube W copies to sort these cycles into different layers and sparsify them without ruining the LDPC property. Yeah, question?
Yeah, to get from step 1 to step 2, you had to make a choice of covering.
Yep.
How much does that matter? Like, is there presumably different choices will give you better or worse graphs?
Yeah, definitely. Like in playing around with examples, you just sort of try some random things and see which one works best, but there may be a way to choose the best choice. I'm not sure what that is.
So there's some combinatorial thing where for each edge for each hyper edge, I could try all the possibilities.
Yeah, and you can also, this is just one choice that gives you kind of this lowest number of edges. You could just put a clique on top of that as well. That will work.
So instead of feedback, how much expansion do you need and what does it depend on?
Oh yeah, you just need, so I should have written this on the slide. Sorry, you just need this Shiga constant in the original graph, this one, to be 1. So when you, this is actually probably a bad example because Shiga constant is going to be less than 1.
So for the graph theory lemma, is log cube known to be?
Yeah, I guess this goes to the lower bound, and I don't know. I feel like our original guess that we should be able to get away with log. Somehow we had this guess that we would need log because like we're kind of expecting there'd be a bunch of cycles of weight log, but then we thought it was log squared for a bit, and it turned out we actually had a mistake. And thanks to Sunny for pointing it out, log squared kind of makes sense because if you had like log of these cycles and there were a bunch of these log weight cycles and they were overlapping like log amount, you thought you could split them up with just log squared layers. But if you really do the counting of what the Friedman-Hastings lemma gives you, it's log cubed. So I feel like you could definitely improve that. But maybe a bigger question is whether you could just have like a different approach that would just bypass this log factor. And for that, I'm not sure. But I think even here, just the sparsification could be improved. Yeah. Well, Sunny?
It's a very fun combinatorial problem. It's log cube right now. I really hope to get it down to log square, but some of the obvious things we tried haven't worked out.
Yeah.
But yeah, please talk about it.
And somehow I remember in film pasting, in their context, log square. Is that true?
Log squared is a different thing. It's not the number of layers you need. It does pop up, which is why we got confused in the first place. I think like log squared is about some amount of like collision, but then when you do this division into different layers, it's actually like a funny procedure where you kind of like are actually you make like a new graph because you kind of remove cycles you've already specified. Yeah, I can't really do justice to it, but it does seem like it's log squared, and that's why we made that mistake. Yeah, okay. More questions about the technical details? Yeah. Good. We're doing pretty well in time. I wanted to just talk about the fault tolerance for a bit. I just talked about the static properties. So like we have this kind of LDPC code, and then we sort of preserve its distance. We add some extra qubits to it, and we go back to the original code, but do we accidentally introduce some logical error channels when you look at this whole procedure of taking this block, deforming it, staying in this deformed code for a while, and then coming back? Yeah, so what is this procedure? It's pretty simple. You have to just sort of, in the proof, we imagine we're idling in this, or doing syndrome extraction in this original LDPC code for sort of D rounds. This is just a sort of a hack on the proof, I think, to make sure because you don't know what's happening before the first step, you don't want there to be some kind of logical fault that comes in along time direction and enters the procedure. I think in practice, you wouldn't need to have this idling, but for the proof, it's there. So you have like D rounds of syndrome extraction, then you switch to this new code, spend D rounds there, and then you switch back and spend D rounds again in the original code. Okay, and this D rounds in the middle code is really necessary. If you're only addressing like one copy of a logical, which is what we're doing, it doesn't matter how fancy you try and get or what properties your code has, you really need D rounds, otherwise there's some error in the original code that can just kind of avoid the logical and, well, maybe an intuitive way to think about it is if you, in one of these vertex measurements, if you have an error on that and it just keeps getting an error every time you measure it, then if you, that will become like a logical error unless you repeat it enough times to catch that measurement, that like repeated measurement error. And so you need to kind of repeat that D times. Good. And then, okay, back to original code. One key point here, I'm going to talk about the space distance a little bit more. Really, you have to worry about like these space and time errors. Like you can have some logical error that has like a bunch of stuff, Pauli's happening, and then there's some measurement faults, and then more Pauli's. But there's this nice property here that essentially the space and the time errors decouple, or you can clean like a general error into a space and a time one, and then you can kind of bound those two separately, and the reduction you get between them is not going to ruin the distance, essentially. So in the proof, we can just treat them separately, which is making life easy, because the time-like errors are very simple. They're just like repeated measurement errors. So they have distance D as long as you repeat D times. How do the space errors work? Well, you have this original QLDPC code with some distance D, and we're trying to preserve that. The main trick there is that if you have like an X-type logical in the original code, and now you have this deform code, you can use the new stabilizers you put in, these vertex stabilizers, to push the X off the vertex support and push it onto the edges. And this is why you need the Chiga constant to be 1, because if you imagine the Chiga constant was sort of less than 1, and you push the X logical into the edges, it might reduce the weight of that and reduce the distance. Yeah, and so the way the proof goes is basically you show like a general X logical in the deform code can be sort of pulled back onto 1 in the original code vertices without changing the distance too much. And then you're guaranteed that that has distance D from the original code properties. The Z logicals end up not being a problem. And here, I guess I'm talking about a CSS code, but you can combine these two steps into treating a like a non-X or Z type logical, a combined type 1. So it applies to CSS codes as well. The Z part of logicals essentially only increase in weight. They just pick up these tails, and so they don't get reduced. Good. All right, so a couple of examples I want to do before talking about magic states. Going back to the surface code example, the way you recover normal lattice surgery is essentially by picking this as your logical you want to measure, picking this as the graph, this just filling in more surface code, and then applying the procedure there, and it just gives you back exactly normal lattice surgery. The final step is splitting things apart. Yeah, so this column scheme I've been talking about, I'm going to talk about a way of implementing it within our formalism that's equivalent. It's not exactly the way it was discovered there, so hopefully Isaac's happy with it. Essentially, what you can do to get something equivalent to the column scheme is just pick a big plane of surface code. So you pick some like linear ordering of the vertices, you pick a bunch of ancilla vertices along that ordering, and this gives you a patch that's like D by D, which is where that scaling comes from. And this will let you do your measurement without reducing the distance. And you can notice that sort of in this graph here, the kind of expansion seems a lot lower, but essentially you have like a bunch of copies of the edges along each sort of tower coming out of one vertex. So that's where sufficient expansion comes from, or like relative expansion in this case. But you can see that, yeah, the scaling of this is kind of much worse than a sparse graph on these vertices, or like log copies of that sparse graph. Good. Oh yeah, and then the final step of that is again measuring out the sort of auxiliary surface code patch. Oh, and I wanted to talk about this cool work. So I said you can apply this procedure across code blocks, but it turns out there was like, well, almost simultaneously with our work, another work by Ted, Thomas, Giacomo O'Connor, and led by Escher Swarup, that gives you a really nice way, among other things, a really nice way of picking, if you know your measurement graph for logical 1 and logical 2, in our procedure, we'd sort of just say, well, sort of pick a random expander onto both of them and sparsify it. There's a much better way to join the two solutions you already have together that preserves the properties you want. And it ends up being very simple. Essentially, you pick like a path in one and another that are the weight of the distance you want to preserve. And then you just join these vertices with a bridge sort of pairwise. How do you make sure you can always do that? I'm not going to go into that, but if you look at their paper, there's this nice skip tree algorithm where you can always guarantee that such a path can be found in the two logicals you're measuring. So sort of moral of the story, if you have solved this problem for two disjoint code blocks, then you essentially, up to the skip tree algorithm, have a solution for measuring the joint logical as well. And the scaling of this extra step is very good. It only goes like OD. You don't need this log kind of overhead. Good.
Sorry,
Mhm.
how did you pair them up? Sorry.
Yeah, so this is like not my work. How do you always make sure you can make such a choice? It's this skip tree algorithm. So essentially you sort of find like a tree basis in one graph and in the other graph, and then you traverse the tree in a way where you always kind of take enough steps forward and backwards so that you can always find short paths to make sure that you keep this sort of LDPC property.
Oh.
Because you could ruin the LDPC property by picking two random paths. And that's what this solves. But yeah, I don't want to talk about it too much because it's not my work. But yeah, it's a nice paper, so I'd recommend to read that. Okay, good. So I told you some examples, and then how do you measure pairs of logicals? Now I want to get onto what about non-Paulis? So in the logical measurement procedure I talked about, there was no need for the logical that you were trying to measure to actually be a Pauli X type. You could just sort of change basis on, say, a Hadamard gate, for example, to turn it into an X-type logical. But the problem with that is it makes your code, if it was originally like a stabilizer, Pauli stabilizer code, it will give you a code now that's not a Pauli stabilizer code if you change the basis of a non-Pauli, say a Clifford logical, into a Pauli logical. And so we can apply our procedure formally there, but we can't give you any guarantee about the properties of the deformed code because you get like a non-stabilizer code, it's quite hard to deal with. Part of this work here, we're returning now to the 2D, the setting of 2D topological codes. So we have like a lot more tools to address the question. And part of this work is literally doing this, measuring, basically applying this gauging measurement to a Clifford operator to prepare a magic state with surgery or generalized surgery. And the way we can guarantee it's fault tolerant is using some cool ideas about anions that are following on from previous work by Hector Bombin and Ben Brown. Okay, so let me try and run through this. I'll give you one example of how this works. There's a bunch more examples in the paper. I'm going to focus on this funny system of two toric codes. So imagine it's like on a torus, and there's a red toric code on this kind of triangular lattice, and a blue toric code on an inverted triangular lattice. And they overlap in this sort of way to make this nice pattern. And I'm going to make each site sort of 6, so there's like a supersite that's like 6 sites from these two plaquettes that are stacked on top of each other. And now my symmetry is going to be coupling these two toric codes together with a bunch of CZ gates. So if you have this sort of transversalish CZ gate that's going from red to blue to red to blue around these plaquettes. You can check, this gives you symmetry of the code, and it has like a non-trivial logical action. So if you apply this to an X operator in one copy of the toric code, the red X along the horizontal, it will produce the Z logical of the blue toric code along the same direction. So it maps X on one copy to XZ, where the Z is on the second copy. So it's essentially doing like a CZ between some logical qubits. And I'm going to gloss over the fact that there's going to be 2 logical qubits per block if we have a toric code, and just focus on the horizontal, on the red X horizontal logical and the blue Z horizontal logical. Cool. So this is like a more complicated looking thing than just like a product of X logical, but it still falls into a bunch of disjoint sites. That in principle, we could change the basis of these sites to bring this into the form of like an X. But we don't need to do that. We can just go ahead and instead of measuring the vertex term that's like X on the logical qubit, or the qubit in the logical and then product of X around that, we introduce this auxiliary graph joining the nodes together, 1 node per super lattice site, and then we measure into these generalized star terms. So any kind of transversal-ish symmetry that just breaks up into a product on sites, even if it's not Pauli, we can apply this gauging measurement to. And in this case, the graph we pick is just simply this like 2D lattice graph connecting these supersites. It's another triangular lattice shown in green here. And the vertex terms are the action of the logical on one sort of supersite with this star term around it of X's. So people have questions about that? It's just like a slight generalization of the star term we had in the previous gauging measurement. Okay, and here, so we could always do this, but you get like some kind of crazy code. This code has stabilizers that have CZs in it, so we can't deal with it with a regular Pauli stabilizer formalism. People have looked a bit into this, so it's not like all is lost. This is sort of this is part of this sort of generalized Pauli-Clifford formalism. People have looked at XS stabilizer codes and XP stabilizer codes, and this is similar. But yeah, definitely a lot more difficult to deal with than Pauli stabilizer codes. But here, what comes to the rescue is physicists' knowledge of these anion theories. So we know that this deform code, and I'm not going to go into it, but it has these non-abelian anions, and we have quite a good understanding of what the faults in this code are, even though we can't deal with them with Pauli stabilizer formalism. And okay, that was just the final step. So the code deformation procedure is still just to deform by measuring these star terms, gives you some kind of wacky code, and then to go back, you measure out the edges in the Z basis, and it will restore you to the original code and measure the logical you want. But in the middle, you get like a more complicated code. But what a lot of this paper is about is really dealing with this thing in the middle. And so here's like a space-time picture. You do this gauging measurement, you end up in this twisted quantum double code, what we call TQD. You stay in there for a while and then move back. Why does this give you the measurement? And the reason is, again, because basically the product of the vertices at one slice in this middle deform code, so the product of all these just gives you back the logical. Okay. And what does this logical do? In this picture, you end up getting this sort of nice topological picture for everything where the X and Z logicals, you can look at their kind of world sheets, and the intersections of the world sheets give you the logical action, where the only non-trivial kind of action is when you have an intersection of a green, blue, and red world sheet, you pick up a -1. And so I'm not really going to go into what this topological path integral is, but it was super useful in this paper to derive like many different versions of these gates and their fault-tolerant properties. And the upshot is only the topological properties of how these logicals intersect matter, and so you get a measurement that just depends on the logical sector you're in. So if you have this logical sector of having an X on the red copy and an X on the blue copy in this way, you'll land in the CZ, the transversal CZ -1 eigenstate. Whereas if you're in any of the other sectors, you'll be in the CZ +1 eigenstate. Okay, and that will give you a sort of funny magic state. By picking different boundary conditions that are more complicated, you can get more standard magic states like T states, but I picked this one because it's got the simplest setup. And let's ignore that we get a kind of funny magic state out. You can still use that instead of a T state if you want. Okay, so the main trick here is how do you deal with the fault tolerance of this procedure? We can't use the same argument we used before. And here we look at a stochastic error model actually instead of this adversarial error model. And what do errors look like in this funny deformed code? Well, you end up getting a bunch of these like Z-type cycle checks that are kind of Pauli things, which are familiar. And then you have these funny X checks. So the X's were product with CZs. And the problem is that these X's product with CZs don't actually commute with each other outside of the eigenspace of the cycles. And this is where the non-abelian anyons essentially come from. So you can think of whenever there's like a Z cycle that gets flipped or it has an error, it creates some kind of defect. But unlike in regular stabilizer codes where this defect is just an abelian thing, like a plus or minus 1 that kind of floats along there, this acts like kind of a puncture in the code, and it can hide other errors. So other anyons can kind of go and hide in that puncture. And so you don't want these punctures to proliferate because they're essentially reducing your code distance. So they're kind of bad errors. And to deal with them, we use this idea that goes back to Hector Bombin that Ben Brown also developed in a follow-up paper called just-in-time decoding. Okay, so the idea is we want to get rid of these things as fast as possible, but we're working in a setting where we're doing fault-tolerant error correction so that the measurements might also have errors. So how do you deal with wanting to remove these as soon as you see them, but also being conservative to make sure you don't introduce more errors by having a measurement fault that is giving you the wrong information? The upshot is essentially you just wait a time that scales like the separation. So you form some clusters given the information you have, and you kind of don't immediately try and remove the clusters. So this is a space-time picture, time going up the page. You keep track of this cluster, and if it doesn't run into another cluster, and you've waited a length of time that's some constant multiple of the width of the cluster, you then are happy that you've measured repeatedly enough times to be sure enough that there's this defect is real, and then you go and pair them up. And when you pair them up, they have this nice property. So this anion model is not like a general crazy non-abelian anion model. It's quite a nice one that when you pair up these kind of punctures, non-abelian anions, it just produces back abelian stuff that you can think of like regular errors. So essentially, once you can remove these tricky errors, or these tricky faults, these tricky syndromes, they just produce a bunch of abelian syndromes you can keep track of classically. Okay, and so what's the real, so if you go and look at the paper, this proof is worked out really nicely in detail, and if you want to learn about the techniques of proving these sort of threshold theorems for the just-in-time decoder, I would suggest looking at that section of the paper, very written in a lot of detail by Margarita, and a great place to learn about this. I'm definitely not going to explain it to you in detail now. I'm just going to say that the key idea comes down to you have this procedure to make these clusters and remove them, but the problem is as you wait, the clusters can kind of join up into bigger clusters, and if that sort of percolates, you're done. And the trick is showing that at a low enough error rate, these clusters don't percolate, and you can get on top of them. So I'm not going to go into any more detail about that, but do people have questions about sort of vague overview of the just-in-time decoding? Okay, so this is really the tricky step that works differently to a regular stabilizer code. Okay, yeah, and sorry, this was just some notation, like these red lines were denoting some non-abelian anion world line, and these boxes are the clusters you're making with your decoder. Good. And then for the experts in the audience, I have like a minute. Yeah, I'll say this. How does this relate to these previous works of Bombin and Ben Brown that I've been mentioning? And in those works, they made this sort of 2D non-Clifford gate by making thin slices of 3D code that has a transversal non-Clifford gate, and then kind of slowly sweeping this thin slice across like a 3D block. So they had these funny procedures that looked really weird to me when they came out. And that's what actually led to this project in the first place. It was like, what is the 2D picture of what's going on, the purely 2D picture of this like thin slice of 3D thing. And the relation is essentially this, I'm going to tell you now. What you have once you're in some slice of this, well, a way of looking at this procedure is that you prepare a thin slice of this 3D code. So you have like 3 copies of toric code, or all the 3D color code is equivalent to that. And you put certain boundaries on the top and bottom to make this into just a very thin slab. So with these kind of boundary choices, you can actually formally say that if this is a constant width slab, it's equivalent to just a regular 3 copies of the toric code. So how does that become or get some magic state in it? You now apply this transversal non-Clifford gate in 3D to the lower part of the slab, and it creates like this sort of domain wall in between the two slabs, and it changes the boundary type. So overall, this hasn't done anything. You've just kind of changed the basis on a bunch of qubits. The trick is then to push this slab forward. You measure out a slice off the bottom in just say the X basis, I think is the right choice. And this restores the bottom boundary to a different type of boundary, but it keeps this domain wall in the middle. And so this new slab you get that has like the same boundaries as the original choice, but now with this sort of funny domain wall in the middle, is known to be equivalent to a different topological anyon model, which is this kind of funny twisted quantum double non-abelian model. And so yeah, if it went over your head, it's fine. This is just about the relation to a previous work. And what we do here is rather than doing this kind of thin slab rinse and repeat procedure to push this domain wall through time, we just sort of stick with an equivalent version of this thin slab as a direct 2D model the whole time. But yes, there is a very concrete relationship. Good, but I'm going to refer to the paper for more about that. And okay, let me just say final comment before questions. Is that all right? Yeah. Good. So Sunny's going to tell you more about how to put these surgery measurements together into an architecture with fixed connectivity. So you're going to see pictures like this. And the idea is basically instead of having an ancilla system to measure one logical qubit, you attach an ancilla system that's capable of measuring any logical in the code block. The conditions on the graph you have to attach are very similar to the ones I showed you before. And then you're going to combine these augmented blocks that now have an ancilla system to do logical measurement together with some magic state factories. But why I wanted to tell you about this was because in the title of the second paper, it's like 2D fault-tolerant computation without braiding anyons. 2D sort of topological computation. And the way that works is one example of this procedure of fixed connectivity. You can go back to your regular kind of surface code blocks with surface code lattice surgery between them. But now we have this interesting thing where we can put in this 2D sort of surface code copies version of the magic state. And so what you get is sort of a purely 2D fixed connectivity scheme for topological computation, so using topological phases all the time, without really magic state distillation. But instead of that, you use this modified surgery measurement to prepare the magic states in this way I was just talking about, which is sort of an interesting alternative to using surface codes with magic state distillation. But okay, it requires more work to see if it's really going to be competitive. Good, so with that, I'm going to conclude. And yeah, like I said, this new results have raised a bunch of questions, but there are even more questions. So, what are really the best heuristics to find these graphs on finite size? Proving thresholds for more general, or how does this procedure modify the threshold of the code when you change to this different code? Looking at lowering the time overhead with single shot and parallelism, and there's already been some work about that. And then thinking about like these non-Pauli measurements beyond sort of 2D codes, because a really interesting direction. So thanks for your attention. I'll stop there.
Do we have questions for Dom?
Yeah, I had a question about this like gauging thing for measuring Clifford. So say you have like transversal Hadamard, like in a color code, and if we apply the procedure, then introducing like H and X check seems like pretty straightforward, but then like the Z's don't they neither commute or anti-commute with the H. So what do you do with that?
Oh yeah, I mean, deriving the code you get. So I didn't really go into it in this case, but the reason I picked this funny example was because the deform code you get is quite nice there. In the example you're saying, you can work it out. It's actually in the appendix of a paper I have with Abnev Prem on gauging permutation symmetries on fractons. Yeah, it's not particularly nice, but you can work out what the operators are. And they end up being equivalent to the example I showed you.
But like, what do you enforce when you try to find the new checks? Like this.
Yeah, so there's like in this gauging formalism, there's like a procedure to sort of find what the new checks are. And essentially you go into the basis of the symmetry. That's why trying to deal with the Z in the Hadamard case is bad because it's getting permuted. So you have to combine the X and the Z flickets into a symmetric operator, and then kind of then write it out in a basis locally of the symmetry. And we have one version of that in the paper with Abnev, but it's not, if you just sort of directly write it out, it's not particularly nice.
Any more questions? I think I have a question. So in the paper by Isha, what was the overhead there? Was it D or was it D squared? Was it joint measurement?
So just for the bridge, the
Oh.
overhead of that part is D, but the overall overhead of like the full measurement system will depend on what your solutions were.
Oh, right. Okay. So it would then be kind of like if you use your scheme, it would still have this log.
Yes, for the full thing.
Okay. Okay. Right. Any more questions? Okay. If not, then let's thank Dom again for the next part. We have another coffee break, and then in half an hour we meet again here for a talk by Sunny.
This solution